Maybe Griffin start with the Navy presentation.
Yeah.
Yeah.
Okay, we can do that. Okay.
So this is covering the I guess do a rough summary. What's this project? What's the intent? What's some status and some updates?
Wait, before we do that, you'll have to enable my screen sharing.
Oh, is it not enabled?
It's not.
Who can share all participants? Try clicking on it. Should work.
There we go. Okay.
Yeah. So what brought you into this project? What are you actually working on? What are you restoring? What's your team? And what kind of what's the status and what are you getting done?
So pretty much this project had commenced in September of last year.
Can
I've
you
been
do that full screen?
Let's try that.
Sorry.
Can you still see my screen?
See your
Yeah.
screen.
There we go. Okay. Well, yeah,
That's fine.
a brief synopsis of this project is I've been appointed as the head operator in charge of a certain vessel in the port of San Pedro in California. This ship is historical in the sense that it had served in World War II, Vietnam, and the Korean War as well. But until recently, it has not really received any attention. It has some repairs that needs to be done. So in that case, I was appointed as the head to repair the radio room aboard the ship. And I will pretty much go through a walkthrough of what I encountered the first time I entered, and we'll pretty much give a series of updates of what has been done thus far. So the picture you see before you is the actual transmitter and receiver equipment that has pretty much been intact since this ship when it was created back in 1944. It consists of 3 transmitters and 2 receivers. Now you can see that the previous people who had managed this radio room, particularly the ham radio operators back in the 1990s and early 2000s, had employed certain implements such as some modern equipment, as you could see in parts of the bottom half of the racks as well as the top, where you could see signal generators and other auxiliary equipment that has pretty much been left there and was more or less haphazardly put together and installed. So my objective was pretty much to remove all of this and get all of the transmitter receiver equipment back up online and on the air. So this is pretty much an overview of the equipment that's before the table. And I'll go through an individual walkthrough. So starting from the right-hand side of the equipment, this is the emergency transmitter unit. It is a 40-watt unit that operates on the HF part of the band, so this is around 2 to 24 megacycles, and this is primarily operated by a battery supply. The battery accommodations, we could see the switches below. If I could zoom in, it should work. You can see the on and off battery switches, as well as the antenna current, the RF current meters, filament voltage, and charging current meters that regulate power going to and fro to this emergency unit, as well as other band selection switches and what have you. The next unit, right to the left of this, is the main transmitter. This is the main maritime transmitter that operates at about 200 watts out and pretty much covers a variety of different frequencies from about 385 kilocycles all the way up to the distress call-in frequency of about 500 kilocycles. And we can see that all of these meters and all of the fixtures attached to the panel are pretty much original. The receiver that's implemented on the bottom is a broad spectrum receiver, and this was not the original unit to this transmitter setup, as this was brought out from one of the cargo holds in the ship during the repair process. But nonetheless, during the adventurous process of repairing this unit, this receiver was ultimately repaired and is fully operational. This transmitter upon my initial inspection, did not have the output tubes inside of it. This type of transmitter uses two 813 vacuum tubes, which are rather robust, but of course they were not incorporated into this unit, so it was a matter of hunting down the right tubes to place into it. The next unit to the left of this is the HF unit. It also does about 200 watts roughly. It covers 2 megacycles to 24 megacycles, similar frequency range to that of the emergency transmitter. But I would say that this unit was the most neglected from the previous use, as we could see that the bottom half of it, where we have our HF receiver, was pretty much removed, and this crude implement of a Yaesu transceiver was introduced. My guess is that the ham radio operators prior had used this digital unit as the main means of communication and pretty much neglected the rest of the setup, as I was able to determine. And we could see that the call sign plaque pretty much hides the oscillator unit that goes to this HF transmitter that was ultimately ripped out at some point in this transmitter's history. I cannot locate this, so this is an ongoing project which there are some solutions to pretty much replace this call sign plaque and reinstall the original oscillator, but that's a work in progress. Nonetheless, we could see all the original meters and other knobs and fine adjustments that are a part of this setup, as well as other selector switches and other components. Going to the next picture, moving down the line, we could see the auto alarm system that was incorporated originally to this unit as part of an emergency detection system that operated on the 500 kilocycle distress frequency, so that certain automatic alarm systems could engage if there was a distress signal called. This receiver, more or less, could pretty much activate and alert the radio operators to engage in communication with any distress vessel, as well as send out a set of distress signals, which was an automatic feature of this unit. This unit that I will zoom in is not original. This was implemented in the 60s, but nonetheless it is very similar to the original unit that was employed during the 1940s. And if we zoom up on this, we could see that there is the auto alarm master switch, which also connects the main transmitter and HF transmitter to the various antennas, so it acts also as an antenna selector switch. And if I move down, we could also see the other parts of the master alarm system, which is all very original, and of course some of the leftover pieces from the previous operators were conveniently shoved into this slot, so that was another aspect which had to be dealt with in terms of the overall repair of this entire setup. So the first part of the restoration process I'd like to draw attention to was the most obvious, which was removing this digital transceiver on the HF unit. That was not an easy feat, as I could not locate the original receiver that went there originally, but luckily I did, as it was sitting in one of the cargo holds of the ship. So upon discovering this, the repair of the new receiver that covers the HF part of the receiving capabilities of this unit was under repair, so we could see the bottom chassis view of this receiver. We could see all the original components and what have you. Most of it was intact. There were some parts, including resistors and other condensers, which were removed and partially damaged from years of neglect and storage. So luckily I had some parts on hand to refurbish this unit. And pretty much it's now fully operable, and I have used it in communication. Now, proceeding with the overall unit, we could see that this is the back of the entire setup, the entire transmitter and receiver unit. Mind you that the angle of this image and the following images are not the greatest, because the clearance of space between the back of this unit and the wall is almost about 18 inches, which is rather cramped, so this is more or less what you could see walking right behind it. Right now, the large coil, which you can see in the forefront, that's a part of the tuning assembly that connects to the main transmitter, and proceeding back into perspective, we can see the new 813 tubes that are a part of the HF transmitter, as well as the other components and electrical systems that are in this unit. And this is a closer picture of the HF unit with the new tubes in it. Mind you, most of the components in this picture were not cleaned up. This was merely a general overview of what I was encountering. But we could see just the overall construction practices and the electrical layout of this unit, as it was pretty common during the 40s and 50s for naval electrical equipment and transmitters and what have you. So upon my initial inspection, going through all of the components, the transmitters, the transformers, resistors, condensers, and other electrical units were pretty much intact. I did not have to replace any of them, thankfully, as they were still in decent condition and likely had not seen operation since, I would say, the 70s or 80s. So most of the repairs that had to be done were cleaning, contact cleaning, and fine-tune adjustments of all mechanical movements and other electrical parts of the transmitter and receiver sets. So that's pretty much the work that was encompassing that. And going throughout the rest of the radio room, despite it being very small, we could see other historical pieces and components which are present near the entrance of the radio room. We could see that there are different signaling bells and voice tubes, speaking tubes that connect to different parts of the ship, including the galley and the wheelhouse. This photo shows some of these bells and the speaking tube, which we could see on the right-hand side, all of which works, although there are some parts that do not work and will need repairs, specifically some of the signaling bells and what have you that connect to the other parts of the ship and to the radio room, so that will be another restoration project in itself. But nonetheless, most of the components are here. And despite this, there are some new implements, switches, and other electrical parts that are not original and really do not have any belonging here. So that will also be part of future restoration projects to remove and pretty much restore. We could see the main electrical box, master switch here in the center of the picture, which pretty much engages the DC supply going from the engine room, either driven by the steam turbines, or as in this case, since we have ship-to-shore power, we're pretty much extracting the DC from the onboard rectifier supply. And this allows for the transmitters and the other receivers to get full DC power. This is a centered picture showing the same components, so you could just see the overall layout of that. And moving elsewhere throughout the radio room, we could see on the ceiling that there's a vast array of messy wires and irrelevant components, including digital tuners and what have you, that were poorly connected to the onboard antennas and other fixtures that were left over by the previous operators. So this is one of the most unsightly units affixed to the ceiling, and in recent efforts this was ultimately removed, as well as with the rest of the coax and other leads that were haphazardly thrown around. This is one of the main switches, antenna selecting switches, that connects to the antennas, which you can see leading up to the antenna trunk going upwards into the ceiling. But you could also see the dangling wires and pretty much the years of neglect left from the previous owners, as well as some other unsightly things that are present. So zooming into the antenna trunk itself, we could see that some of the coax connections left on the left were poorly installed, and those that will have to be replaced, but nonetheless the copper tubing which connects to the antenna bushings atop the antenna trunk are still present, and they still are in decent condition, although the antenna trunk itself does have some damage, rust damage, and holes that are present. So deck department currently is refurbishing that so that to make it watertight. Otherwise, rust will pretty much creep in to the rest of the antenna trunk and ultimately into the radio room. And this is a closer view of the connections going to the antenna. Unfortunately, I was not able to get a clear photo of the exterior of the antenna trunk and the insulators that connect the antennas because right now the deck that's atop the radio room is a bit unstable, and that is where the site of deck department's work is being conducted to repair that so it is safer to walk on. So we can only see it from a distance, and I cannot take any pictures of it in person, unfortunately. But that's pretty much the compartment of the antenna itself, and working our way into the units below the transmitter and receiver sections, which are covered by panels, we could see the main source of power which delivers the high tension supply to the plates of the vacuum tubes on the transmitters, and this is the main motor generator setup. This one was installed, from what I have heard, around 2010. It was fully refurbished, and to this day it is operable. I've used it myself and I have maintained it to the best of my abilities. So luckily that much of the whole setup is completely functional. We could see the fuse assemblies and other networks behind the motor generator setup, and of course some wires and some connectors which are not original and were poorly installed, so that is another part of the restoration project, which was tackled, I would say, within the last 2 weeks, so luckily that much has been finished. And this part, of course, is connected to the main supply going to the motor generator and as well as the other parts of the transmitter receiver setup. So this was also partially refurbished, and we could see that it is a bit complicated with the terminal strips atop, but luckily that was mitigated and some of those wires that were newly implemented were removed with more adequate wire, as those are artifacts of the former people who pretty much operated the setup. But nonetheless, this is just a general overview. These are other components of the power supply itself. These are essentially relays, which you can see on the bottom, circuit disconnects, which do need to be replaced as they are fairly tarnished and are not operable. But luckily, we have located some adequate components to replace this, which was present in one of the cargo holds of the ship. And this, of course, is a view of the cables leading in to the ship, carrying the DC supply, going to some of the fuses and being dispersed to other parts of the unit. And of course, there's also a slight mess of wires that was still present from the previous owners, so that was fortunately taken care of within the last few weeks. I do not have any photos of that, unfortunately, as lighting was quite poor, but you can imagine that most of this was tackled and pretty much fitted with the correct wiring and done so correctly so that it looks presentable and it's reliable. This is a closer view of the terminal strips and fuse assemblies, which connect the main power to different parts of the transmitters. And moving our way to the right, this is the power supply that pretty much connects to the main receiver, where it has its own rectified power supply, but it's also able to be supplied by auxiliary batteries, of which are encased right below it. And this also incorporates the power supply going to the emergency transmitter, which you could see partially below. That's the battery compartment bay. And of course, the battery compartment bay, which you can see also here in a clearer photo, those batteries have to be isolated and located, and eventually the emergency transmitter will be fully restored and operable. So that is probably one of the last units that has to be fully restored, but nonetheless, in physical condition, it's fairly all right. And moving through the rest of the pictures, some of the initial restoration procedures done was pretty much directed towards the first transmitter, which was the HF transmitter. In this case, we see that the panel is pulled down below. We can see all the individual parts, the coils, selector switches, variable condensers, and what have you. So, like I said, most of this was present, most of the components were present, and there wasn't that much work that had to be done, luckily, so most of it was cleaning and pretty much making sure that all mechanical components and what have you were fully functional. So this is a closer view of the components and what is present in its cleaned state, more or less. All contacts were cleaned. Tube pins, tube sockets, bars connecting the variable condensers to other components were all cleaned. Anti-seize and other solvents were used to make sure that all these connections are durable and will pretty much last for many years to come. This is a view of the variable inductance coil, which was the site of probably some of the most major work on the set, as there's quite a bit of tarnish, as you can see, as is still present on the middle half of the coil. So this photo was taken during the half process of restoring this coil, but now it's completely clean and is able to move freely. It's no longer seized, so that was, I would say, one of the main points to be addressed on this HF transmitter. But despite all of this, the HF transmitter is fully functional and operates as intended. So that was another project which pretty much was completed and finalized. Another project to be done was the removal of this crudely implemented box, this rack, which was introduced by the previous ham radio operators. It was pretty much a variety of a mess of digital components and what have you that had no belonging in the radio room, but nonetheless it was implemented just for the sake of convenience for the former operators. And upon seeing this complete mess, the main course of action was to remove this entire system, this entire rack, which was poorly constructed, and pretty much liquidate all of the components that were present and make space for originally what was intended to be a table here, a small table, so that to also give space to the rest of the transmitters and panels that moved downwards, as this rack was right in the way and, like I said, had no purpose or belonging. So luckily that was removed and is no longer a problem. Another part of the restoration project was to pretty much remove all erroneous wires and dangling pieces which were present throughout the ship and specifically around the radio room, of which coax and the like were going to and fro the radio room to poorly constructed antennas and other parts of the ship thrown around and neglected. So that was another major aspect to be undertaken, was the removal of all this auxiliary wire. And we could see that leading up to the antenna trunk here, we could see that some of these wires are just dangling in the open air, disconnected and frayed. So this was ultimately removed and cleaned up. And like I said, deck department is continuously working on the antenna trunk and other exteriors relating to the radio room and what have you, to pretty much remove and mitigate rust and make sure everything's watertight and in tip-top shape. Now, following the restoration of the main transmitter and the HF transmitter, all components and all systems for these transmitters were pretty much finalized and repaired within the last couple of weeks, and we could see that in this case we are looking at the HF transmitter operating. This is a backside view of the tubes and the assembly in functional and operable condition, with the new 813 tubes implemented and pretty much most of the contacts and other components cleaned as best as possible. The transmitter itself is putting out roughly about 200 watts, give or take. The actual power going, the radiated power going into the antenna has yet to be measured in terms of RF current, as there is not a antenna current meter present on the panel, but nonetheless that would be a fairly easy feat to measure. But like I said, the main objective was to get this transmitter up and running, and it now is. And of course, the main transmitter that operates in the low frequency range of about 300 to 500 kc is also operable, as shown by this photo. And excuse the poor angle, for the size and space constraint is rather limited, so trying to extract a decent photo is a bit difficult. But nonetheless, all the units and all the components of this transmitter are completely functional. And the main purpose of this transmitter is to assist in further telluric research and experiments. Given the frequency range, the power output of this transmitter, and the conveniently low impedance earth that this transmitter cooperates with. So future experiments involving various coil designs and other telluric research will pretty much be operating with this transmitter, as well as the other HF equipment on board, to facilitate this research and development. And this is another view of the main transmitter. We could see the 813 tubes operating, and we could see the viewing screen that's in front of it, so that you could see the filament glow essentially from the front view or the front panel of the transmitter, which this photo shows partially. And we could see that all of the meters indicating line voltage, filament voltage, plate voltage, and what have you are operating. One of these meters had to been replaced as it was not functioning. But essentially, when the telegraph key is keyed down, we get an appreciable antenna current. Our cathode current is also respectively shown when the key is pressed down. So this entire setup is operable and functioning, I would say, for the first time in a couple decades. So this has been the long process and restoration work of this transmitter that is still ongoing to present day. Like I said, the emergency transmitter is still the site of repair work, but nonetheless the main transmitters are fully functioning, as well as their counterpart receivers. And of course, just for the sake of historical preservation, this is also a benefit to the ship and the organization which governs it, as they now have a more or less functional radio room that's free, almost free of irrelevant material, and pretty much set back into its original operating conditions. And future work that needs to be done on this transmitter is pretty much being assisted by a handy manual that was produced by the Radio Marine Corporation of America back in the 40s and belongs to this unit. It's a Model 4 unit, and in this manual, detailed information as far as schematics, tolerances, and what have you are given. So this is a major piece of assistance in the restoration of this equipment, as well as the radio room. And pretty much the layout of the radio room is as follows, as expressed in this diagram. I could zoom in as much as this, but essentially what this diagram is showing is the future layout of what's intended to be done with this radio room, granted that that previous plywood and aluminum rack, which was removed. A convenient and more proper table will be implemented there in the corner, as shown in the corner of this drawing, as well as a proper filing cabinet and other materials which are not exactly crucial to the radio room, but do aid in its overall practical functions. So that's why it is a benefit to have this manual, and like I said, pretty much assists in all operations going on in the radio room. And that pretty much concludes my presentation of what has been going on aboard this ship and I look forward to further development which transpires and of course which will assist in future research. So at that point, I guess I'll hand it off to Connor or Eric to.
Well, let me just interject here. So at any rate, probably a lot of people are wondering, what does this have to do with what's going on here or research in general? Well, my involvement with RCA back in the beginning in the 1960s with the Radio Marine Corporation, KPH, was in communications with this ship and that equipment. Now, in 1970, when everything started to take the big slide, RCA had commissioned me to develop an alternative form of communicating with these types of vessels, and of course more modern ones and foreign vessels and all that, to make the satellite, the appearance, how would I say this, the new appearance of satellite and what have you types of systems that were at that point less than economical for ship owners and what have you, and to come up with employing either the Alexanderson system or the Tesla system to produce a superior means for ship-to-shore communications. So basically, things didn't work out in the long-term history to get this work done. The various forces that are now being combated on a larger scale had infiltrated the RCA station and laid waste to it. And now it's the operating equipment is just a ham radio club pretending to be a maritime station. So at any rate, the antenna that we just finished here, the pole pair antenna, will have two aspects to it. One will be in the audio frequency band, which is basically ultra low frequency and very low frequency from 300 cycles to 15 kilocycles for the Earth signal reception regarding the Earth ionosphere waveguide. The other one will be at 300 kilocycle to 1500 to maybe 3000 kilocycle. In other words, 0.3 to 3 megacycles per second. And that will work in tandem with the equipment on this ship. And then with the telluric test platform, we will build the Alexanderson potential coil, which Griffin already has a model of. I don't know if you have a picture handy or not, Griffin, but then that will be used to transmit to the ship, and then that will further verify and quantify the science and engineering of converting from the normal electromagnetic modes of propagation to the modes of propagation as either telluric or longitudinal in one form or another. So that's how Griffin's project fits in with what's happening here in Tonopah.
Okay.
Well, I have a presentation, or really it's a overview of the Alexanderson antenna that was filmed sometime last year. So I guess I'll show that now.
Okay.
And then, like I said, Eric, you want me to pause or anything, just let me know. So.
I'm Justin Miller with EPD Laboratories. I'm here with Eric Dollard at the end of our summer session 2024, and we're going to do a complete demonstration pole by pole of the entirety of our facility. We're currently at the location of the seismograph mine, and this is a good place to do an overview. You can see our hilltop terminal shack in the background, and you're looking over the extent of the antenna field. So we're going to go ahead and sequentially, piece by piece, starting at the other end at the terminal shack, demonstrate the entirety of this facility, what its purpose is, when we started, historical context. We're going to go through piece by piece and do a pretty thorough documentation. Here we are at the hilltop shack. This is our terminal shack and our dead end
terminal pole for the line, open wire line, for this point. 2024, we're here at the shack. 37 Bravo is installed. So Eric, you want to talk a little bit about what's going on here?
Okay, so this is the end of the line. And these are the natural electrostatic signals that exist between the Earth and the ionosphere. So right now, our bandwidth is that of basically FM broadcast quality. So there's quite an arrangement of signals. Ultimately fairly quiet right now. There's nothing really going on other than lightning. If you want to get more of the signals that come out from inside the Earth, you got to tighten up the bandwidth a bit, and then we go to 3 kilocycles. And that eliminates a lot of lightning crackling. This is where you hear the signals that everyone's always striving for, the whistlers and all the strange twinging noises and what have you. That starts at sunset. If it's acting like that during the day, it means there's going to be an earthquake. Otherwise, it normally starts at sunset. So right now, this is the time of the day that the signals are at their absolute weakest. So we still got 20 dB to go yet on gain. So we're doing okay there. So what I tend to do is make a stereo version of this where the 3 kc and below comes out of one channel, and then the frequencies 3 kc and above becomes the left channel, let's say, where the other one was the right channel, and that gives you kind of a stereo idea of what's going on roughly, because the higher pitches tend to come from outside the Earth and the lower pitches tend to come from inside the Earth. So I learned all these things at Landers with much more sophisticated setup, so having learned things at Landers has made it very helpful to do this right, because just because you hear something coming out of the speaker doesn't really mean it's there. It's the impulses are incredibly high amplitude, and they, even though they don't show up on the meter, they get into the set and they cause intermodulation, distortion, and make noises that aren't signals. So in general, with the material that's available to the public presently, a good share of the signals that you hear coming out of the headphones or the speaker are phantom signals and have no actual physical existence because of transient overload. It takes very difficult amplifiers to amplify that stuff, and this thing was not intended for that. So it was intended basically to kind of lock on to a specific signal and not deal with immeasurable transients. So if you keep your indication below 10 or 15 dB of the threshold point, then you're pretty good to go with a clear signal. So the problem here is all these different transmitters and what have you, of course, overwhelm these devices, because this thing is operating at minus 60 dBm and these are operating at about plus 20 dBm. So the signal power between this rack and this rack is about 1 billion to 1, and that makes things difficult. So we built this back here. So this is a radio frequency filter that terminates the line, which we will follow out, and then delivers it to the measuring set without any of the 144 megacycle RF on it. And that worked out pretty good. And then same thing with the power leads. We go through basically another filter, low pass filter. These things are all designed to filter out any frequency below about 20 megacycles. And then for the power, and then it goes through these feed-through capacitors that shunts it to the chassis, and that pretty much takes all the RF out. So we managed to get this compatible. And I want to point out that most of the gain that's in here is actually going to be down in the repeater cabinet. there'll be two of these in tandem. The one down there will basically receive unbalanced, and this one will take the signal that's pre-amplified by that and convert it to balanced and amplify that up to a level where it can be connected to the speaker. So part of the RF compatibility thing is we have a point of, it's called a point of zero potential here, and the room is electrostatically screened so that inside this building, that is the point of zero potential, and that's what everything grounds to. See the copper lead going to the racks, all the coax. Anything that comes in has to come in to a shielded connector with the shielded grounds to that plate. So that's the point where everything is brought to an equal potential, so you don't end up with all these RF currents flowing around in the rack and what have you, playing havoc with everything. And that's kind of a big difficulty when you're doing a setup like this, where everything's got to be all jammed together in the same space. But that's the way it is in the stuff I learned in the Navy. So if you think this is bad, try CIC in the Navy ship, and boy, you really got some interference problems. Of course, it's the same thing up on the pole, but we'll have to wait till the wind stops before we can go out there. But all that stuff had to be made compatible, even though it's not compatible. So there's just no way around it. So all these various techniques were used to minimize one thing from feeding into the other, methods of neutralization and what have you, and there's just certain flat-out impossibilities when you're dealing with ham radio stuff, because it's never considered in a ham radio installation. So we had to make like special grounding electrodes and what have you. So that was a rough deal to put together. So we'll have to wait till this little mini storm passes before we can get in depth into that.
All right.
So this was a little more complicated than just running a pair of wires. There's a lot of little considerations that go into this stuff. So the first complication is the electrostatic potential at the cabinet had to be kept the same as the electrostatic potential of the shack at that point of zero potential, which I showed earlier. So the wire up on the top on the spool insulators is the conductor that basically galvanically connects the shack to the repeater cabinet. So no dangerous differences of potential build up due to lightning surges in the ground in the area. As far as carrying any heavy current goes in a heavy strike situation, it doesn't really accomplish much for that. But there's no way to really economically deal with that. Now the two conductors on the cross arm, that's a balanced line pair, and because it's a balanced situation, it's important that both sides remain symmetrical. And the addition of that neutral conductor tends to throw the thing out of balance. So that's why the neutral conductor is placed that far away from the pairs. We can't just stick that thing on the cross arm next to the other conductors, or we get an incredible imbalance and noise would just be permeating the system. So in this case, if the distance of the extraneous conductor is significantly greater than 3 times the spacing between the two conductors to be interfered with, that's a fairly acceptable spacing. And ideally it should be in the center, but that wasn't really practical in this situation and not absolutely necessary. And the line's not going far enough. Otherwise, the conductor on the top would have to be zigzagged back and forth on sides every alternate pole to keep it symmetrical with the transmission conductors. Possibly in the future, 2 more conductors would go up to create 2 balanced lines on either side, but that still causes a pretty close coupling with no transpositions, and I don't really see an immediate need for that. Now, the advantage of having that neutral conductor is then the DC power to run the equipment in the repeater cabinet then has a ground return for the phantom off of the 2 transmission line conductors. And when we get down to the cabinet, I'll show how that works. So we can get power and signal to and from the shack with just the 3 conductors configured as they are. There's the usual electromagnetic compatibility problems. Is you don't want the antenna signal coupling into the transmission line and feeding back around the amplifier, and the neutral tends to be susceptible to bringing in external interferences, and so there's a lot that goes in on how you set the conductors and what they terminate on and how you space stuff and all of that. It's not just, you don't still simply throw this stuff together, because spacing of the pair determines the impedance of the line. You got to keep that constant. You can't have one conductor getting longer than the other going around a bend, or that creates an imbalance, and then that length of wire that's gained or lost in the bend becomes an antenna length. So, and then as we'll see later on, you actually have to take the pairs and you have to keep turning them every so many poles, so that one conductor isn't sitting too close to the power line while the other one's not, because then that's going to be antenna current into the power line. So there's a lot of unseen engineering that goes into almost everything that goes on out here. Sometimes it takes me weeks to figure out how we're going to fight the problem and get what we want with the limited materials we have on hand. But we're doing it. It's all going together. Okay, so right now the outside pairs, the phase shift is 180 degrees, which is called a transposition. So the position of the wires is simply reversed. But in the center section, that is ultimately where some kind of network goes and then connects to the ground. And we won't be doing that at this section, because there really is no electrical ground here, and we don't really have in order to keep this close a spacing would be uneconomical because these materials are so hard to get. So basically we're just going to go through here, but it would also be, the pole pair would also undergo a 180 degree shift here ultimately, but right now it's just going through. So it's mechanically dead-ended here because I did not want that dead end load on the ridgetop pole, because it's already got enough problems surviving up there. And we can't really put the necessary guys in up there without it being in a place where somebody would end up out here drunk in their pickup truck and smash it and tear the pole down. So we cannot have a big dead end load on that pole. So basically this is doing the dead ending down here. That's why there's the double arms and the guy, because everything that's going between here and pole 49, that mechanical load is taken up by this guy, and none of it appears on the ridgetop pole. So these are the complexities of this particular location on the line.
Pole 45, this is the hilltop pole. This is where the line changes direction, and the wind's picked up, so I'm hiding down in the shelter of the pickup truck. So from this perspective, it's hard to see that this is a corner pole and it changes direction, but you can just take me on my word that it is. And so corner pole, change of direction. This required guy anchors in 2 directions to take up that load.
Well, hey, let me get, so the guy anchor straight out was the original one. And what it did is it took up the tension of change of direction. But it was just a cable going straight through. There was no dead end. This one has a dead end load. So we put this one guy in here to take up the dead end load on one side, but we could not do that on the other side without it being in the road. So that's why, as we've shown, we had the dead end at pole number 46 down below in the lower area. You can see that. So that guy there is taking up most of the dead end load, so whatever dead end load is left up here will basically resolve itself into the corner guy.
Pole 43, we skipped over pole 44 because it's really uneventful. Existing pole, we just put a cross arm on it. But this pole, now pole 43, is also loading section 6. This is pre-existing pole, pretty scabby, pretty old pole, but also stout, mechanically stout, such that right now we're using this pole as our temporary dead end location for our reception structure. So that's the significance of this pole at present, is that it is the end of the antenna. And so this is a permanent dead end, guy anchored, that we'll use as it's a loading section, so it will always be a dead end pole in whatever incarnation of the build. But right now, significantly, it is the end of the antenna. This is as far as we've built this open wire reception line to this point. And Eric, you want to talk some more about this?
So that basically, so the Alexanderson loading sections are the even numbers. So this will be, being that pole 8 is determination, and pole 6, this will be the first place that the Alexanderson antenna makes contact with the Earth. So there actually will be a network that intervenes. Rather than just reversing the wires, it'll actually transform them dimensionally and introduce the ground element, which has to be a borehole 30 feet minimum in the ground that capacitively couples into the earth. So basically it'll be an earth capacitor. There'll be a plastic pipe, and then there'll be an internal electrode. To start with, we'll probably just use some ground rods in the wash, but these grounds are static grounds. They're not galvanic grounds. So it's not desirable to have ohmic contact with the environment, only capacitive dielectric contact. So one of the big expenses will be at every loading section we have to drill a hole, preferably about 60 feet into the ground, and insert a pickup electrode in it. And that would be its own, that would be rather a costly operation. So to start with, we're just going to use this as a capacitive element between the ionosphere and the Earth, which will be just the pole pair itself, and then at every loading location, there'll just be a 180-degree phase shift. The wires will just cross.
Pole 41, loading section 5. Eric wanted me to set up this shot to demonstrate the length of a loading section. You can see Eric's down there by the car in the pickup, and that would be loading section 4. So 3 spans to a loading section, and we'll go down there and have Eric give his description. Loading section 4, and we just went and skipped those 2 intermediate poles back there. Eric, go ahead and talk about loading sections.
So this will be the next loading section for the Alexanderson antenna. So the pole pair, which is the pair that's in the middle of the cross arms, will be electrically interrupted here and then brought down to a cabinet, another repeater cabinet, where the electrical and electronic components will go to alter the phase and the amplitude of the signals on the pole pair. So now there's, in the final form, there's 2 carrier pairs on the outside of the cross arm, and ultimately they're supposed to be interrupted electrically also and appear in the cabinet. So inside the cabinet is a banana plug matrix that determines how the wires are going to be configured, and then that connects to a Western Electric patch bay, where then you can plug in, various amplifiers or filters or any of that type of stuff that's inside the cabinet. Or even you can patch all the pairs together and run the signal round and round and round, or you can run a regular telephone line all the way up in the shack and have a ringing telephone up there. So this thing is adapted to be any particular form, not get tied to one configuration or another because of the massive investment of materials and what have you. It has to be multi-purpose. But of course that's complicated. So to start with, if the outside carrier pairs go up, this will be a point where they have a transposition and they just get reversed 180 degrees and continue on. There's no thought of interrupting them at this point because that's pretty far down the line. So we'll just transpose them and bring the pole pair down because it's the pole pair that's designated to be the Alexanderson loading section. So basically a loading section, as you've seen with me standing down here and with Justin filming from up in the top, comprises 2 end poles and 2 middle poles. So the inductance and the capacitance of the electrical conductors enter a network which modifies their phase and separates the transverse from the longitudinal and gives the ability to electrostatically have a true monopolar single-phase electrode in the ground from which to receive. The Alexanderson design is rather remarkable. This is an extension of it that was not invented by him, but he came up with the basic plan. So there's only 2 of these antennas ever built. One was in Bolinas, California, and the other was in New Brunswick, New Jersey. Bolinas call letters were KET, and the New Brunswick call letters were WII. And those were 2 stations that were seized from Marconi by the United States Navy and turned into a true Alexanderson form of transmission system. The only surviving station is actually not the fully developed form. That was the one that came later for RCA, and it does not do the things that the Bolinas and the New Brunswick stations did, which was actually be able to create a situation where there was no wavelength on the antenna. So Alexanderson designed a number of antennas for RCA on that principle. So basically, the loading section is not just the wires, but it's the network elements, inductors and capacitors and what have you that are connected to the ends of the wire, which extend it out. And what happens is at every loading section, the phase, which is determined by the propagation velocity to get from one pole to the next, is neutralized. So that lag in time that it takes to go from this loading pole to the next loading pole, the clock is turned backwards. So the net result is the whole antenna oscillates in unison and has no wavelength, and that's why it can be used for such very low frequencies. So that's kind of sums up what these are all about. Well, actually, there's one more. Mechanically, there is no interruption. So the force on one side equals the force on the other side. It has to be on spool insulators to conveniently make the break rather than on a pin insulator. But ultimately, the stress on both sides is equal, so we don't have to double cross arm and we don't have to guy, except if we have a temporary termination while we're constructing the thing, we have to tie it off to a fence post stake. We'll see some of that further down the line where we were experimenting.
Pole 35, loading section 3. Shack at the hilltop for reference. Pole 29, loading section 1.
So here, the pole pair is just going to go straight through, possibly with the transposition, but the carrier pairs are transposed here with these special brackets that twist the conductor over on itself so that the next section of line is out of phase with the preceding section. And what that does is, you can see this power line off in the distance here. This is going to be problematic, so that's why we couldn't go any farther with the antenna, because we get closer and closer to this. So the transpositions tend to cancel that proximity out, because if you didn't have them, one wire would always be closer to the power line than the wire next to it, and you would create an imbalance, and the hum could get in from the power line quite readily into the transmission. But if every so many poles you reverse the wire, then that equalizes that out. Then the other conductor has exposure to the power line, so when they reach the end, they subtract in the repeating coil.
pole 27 now. We're getting close to the town end of the reception line.
So this is the first pole going the other way on the antenna. We're at the other end now, so we're looking backwards. So the cross-arm configuration, these were carrier pairs. So that's what basically the insulator configuration looks like. The insulators are different than the pole pair. The pole pair insulators are always the double petticoat wood pin type of insulators. But these are called type CS insulators, and they go on a special metal pin that only fits them. So the insulator is no good unless you have a special pin. These insulators are good almost up into the 1 megacycle range. So that's why we call this the carrier pair, because this is the one that would carry, those are the ones that carry the radio frequencies, and then the pole pair carries the audio frequencies. That's the standard Bell system configuration. So carrier pairs have to be tighter together, and they can't have pieces of wood and things sticking in the space in between, because that would disturb the wave flow from one end of the line to the other.
Pole 26 now, and this is our terminal pole we've been describing. This is the end of this reception structure nearest town, so this is obviously the other end of the line opposite the shack.
So that's the pole pair will end here, and the outside pairs end here, which we've already experimented with. And the main terminal cabinet will be associated with this pole. So this one's going to have to be a rather large one to accommodate the apparatus, electrical and electronic circuitry necessary. And then this pole, in essence, will be a repeat of pole 49, or the end of the loading sections, loading section 8, and the line to the shack. So there'll be antenna lines on one side of the double arm, and there'll be transmission lines and power on the other side of the double arm, and they will come down into the cabinet. And there'll probably be some kind of future antenna arrangements here, so we have to leave provisions for that. So basically, this is from this point on, the next juncture in the line is the turnoff to the mine, which is basically going to take the place of what's going on in the shack, because we have commercial power available there, and the seismograph transducers are there and all that. So that's going to be actually the command post for the whole system, so to speak. But ultimately, the line in its entirety and a pole pair basically goes all the way back up to the border of the town, and then from that point on, either we have to continue on a cable TV right away, or lease lines from the phone company, or that's still not quite determined yet, but there are a number of options available. So that's that point is 26 poles away, and we're going to continue to that point.
Well, and I'd like to take the opportunity to point out how all of this functions as one facility. This is one system, all of the different pieces. A lot of people don't seem to fully understand how the shack interfaces with the seismograph, interfaces with the long lines, why we need to transmit that back to town. It's one system, so there's a lot of very complicated pieces, which is what we're illustrating with all of this. And we're also showing sequentially how we're going for the minimum, what we would call, minimum viable result to show a demonstratable functioning system, right? Waveform on the scope, audio out of the speaker.
And something on the internet.
And something on the internet.
So basically, as this antenna evolves, its appearance on the internet will become more developed. So ultimately, it will be possible to get an old Navy submarine receiving set, which you could never afford to build an antenna for, because you're looking at that here. And through your computer, you can plug your receiver into this antenna and avail yourself to its reception capability all the way up into the broadcast band.
Pole 26 grounding demonstration.
So this system requires a really exotic ground system. Part of the problem is that the ground is actually now hot because that's what you're picking the signal up out of. So you can't use it to ground other things anymore. That's what we deal with at the building with the Tesla transmitter is we can't use the adjacent tank and station ground the way we would like it because we're transmitting into the ground via the adjacent tank and the RF gets right through. So basically there's three grounds here. There's the one that's the line of the ground rods, and that's the signal ground. That's where this antenna makes intimate contact with the earth. It's the earthing terminal. So because there's some kind of underground body of water here, this seems to be an absolutely excellent place that you would never expect to find in the desert to ground. Now we have another ground that's a cathodic ground. That's the one that's terminated at the base of the pole here, different sections of it. That's for the lightning arresters. That doesn't connect to ground rods. That's laid in a trench filled with magnesium sulfate. So what it is, it's an anode, so to speak. And that will discharge the lightning off of the lines via the lightning arresters, which are up on the cross arms. And then we have a third ground over here, which is simply a ground rod at the base of the pole, and that's the safety ground. So if you happen to be leaning on this thing and lightning hits the line somewhere, the potential here has to be that of what's under your feet. So we have another ground rod here so that the cabinets and what have you will ground locally, so there'd be no way that you could get blasted by a difference of potential between your hands and feet, because that's often what will kill you in a lightning situation. Is what comes up one leg and goes down another leg will end up killing you if you got the wrong gradient. So that's the lightning one is hanging on the pole there, so that will go up to the lightning arresters, which are those little square units up there on the cross arm. We might use the bigger aluminum can ones at some point, I'm not quite certain. And then to start with, two transmission lines will leave this point to go back to the mine. One for receiving from outside the earth and one for receiving from inside the earth, which will be terminated here by the configuration of this antenna and the boreholes in the ground. And what comes off this power line that causes problems, and so there's still a lot of experimenting yet. But this is the end of the antenna system, and everything from this point on is transmission, either back into town or back to the mine, or from the mine up to the shack, or from the town to the shack, or what have you. It's all patchable. It can be configured in any manner. At each of these terminal locations, there'll be a Western Electric jack panel so that any pair can be end to end. You'll have that level of versatility.
In this video, the pole pair was not up yet. So presently it is up. So that's what Connor's going to show you briefly, is some of the highlights of what we went through to accomplish that.
Gotcha. There we go.
Okay, so we had a work episode from December 4th, December 11th, 2024, and basically we ran the pole pair from pole 43, which is right around loading section 6, all the way back to pole 26, which is what you saw at the end of that video. That's approximately 3,270 feet. So as far as the overall conductor that we ran, being that it's a pole pair, that was about 6,540 feet of copper weld that we ran in this last episode. So anyway, let's get this going. Eric, you want to speak to this, and I'll kind of go through the slideshow a little bit.
So this is where we're taking the experimental materials off, and I think this is the one that we had to remove the transposition brackets, right?
Yeah, exactly. So
yeah, so that, as I'm sure Justin can identify, is a very dangerous situation. And we've had some rather frightful episodes in doing that out in the middle of the desert because a cross arm can get away from you, and then all of a sudden those transposition brackets are big iron claws heading straight for your head. So basically, it's my responsibility to make sure that there aren't any mishaps and that whoever's up on the pole doesn't end up dead on the ground. And which means that I can't make any mistakes, so I better damn well know what I'm doing. And it's just as scary for me as it is for the person up on the pole in the long run. And so I think these are all still shots of, but because we're doing this with the ladder and not a bucket truck, it's hard to get out to the end of those 10-foot arms. So the safest way to deal with it here was to loosen up the cross arm and then bring the transposition bracket into a position where it was safely accessible and then take it off. But I had to be guiding this thing with ropes down on the ground, so there wasn't any possibility of it swinging around and clobbering Connor. Justin and I went through one of these episodes out on the Death Valley Shoshone line, and this thing got loose. Do you remember that, Justin?
Oh yeah, I recall that quite vividly.
But that's what
Hard to
the
forget.
rules were for, and there was no mishap. But I about filled my britches on that one, and I don't know what Justin's underwear problems were, but they
Yeah.
were close. So that's what I want to point out is none of this is easy. It's all very dangerous. And, even though Connor's busting his ass up there, I'm busting my brain down on the ground to figure out how to get all this together and to keep all the tensioning equal, with the minimum amount of tools. And Connor's kind of learning as he goes. So it kind of keeps the adrenaline boiling on my part, and probably on Connor's part too, because he's clinging to the pole 20 feet in the air with several hundred pounds of tension on either side of the cross arm. So that's kind of what this particular image was about. So
Yeah.
you can see he's got the transposition brackets off, and I think I don't know what's next. I'll have to see what's next.
Yeah, and I could speak to some of this as well. This is the same pole, just view from up top after the dead end insulators are put on. So in preparation of stringing the wire, you can see our buddy Chris down there on the ground helped us out for a day. So give him a little shout out. Here you can see the insulator pins. We had to build these wooden sleeves, go around it so it fits snug in the cross arms. Just kind of trying to show the process here of how all this sort of goes together. So wire reel machine, we're using some pretty outdated equipment, I guess you would say, but doing it in the classical fashion. And then, Eric manning the wire reel, pulling out the conductor. Here you can see the grips that we use to hold on to the copper weld, which then gets carried up over the insulators. So let's see, this here is this is like 4 poles away, or actually more. It's more like 6 poles away. So it's 2 loading sections. We're going 2 loading sections at a time as far as stringing this all up. So what you actually have to do is you have to make these terminations on either end on these dead end insulators, as you can see here. We put on these preforms. And that secures the conductors on either end, but once you've done that, you still have these conductors, that are basically hanging down to the ground. And you actually have to carry those conductors over the cross arms. Let's see, I think I have a short video here. Shows that process. Just mute out the noise because it's unnecessary. But so, as you move down from the dead end, pulling these conductors over the cross arm just gets more and more difficult because you have more and more tension on it as you go. So you kind of see I'm using this extension pole with a hook to carry the thing over, and yeah, it's quite the effort now. Physically, it's a lot of work, and then like Eric was pointing out, it takes a while to for him to figure out how we're going to go through this whole process. So so a lot of trial and error and a lot that goes into this whole process. It's really not very simple, and like he's pointed out, we don't have a bucket truck or anything, so we're just doing this with really simple means and old equipment. Of course, we're being as safe as we possibly can, but still, there's a lot of risk involved. You pretty much, when you're up on that pole, you can't make a mistake. So, let's see here. Okay, this just shows kind of the rigging that's involved as far as getting the tension on the conductors. So just trying to demonstrate that point. You actually have these come-alongs, which are essentially pulleys. We're literally using pulleys to get that tension on the line. And it takes a while to get that tension just right, and then both conductors need to be at equal tension. So it's a lot of back and forth, up and down the pole, somewhat complicated. And here you just see a termination section of the antenna at dead end. So we have these dead end insulators at every even number loading section. So, and eventually, as was pointed out in that previous video, we'll actually have leads coming down from these dead end insulators into a cabinet where Eric can then, put in various equipment, inductors, capacitors, relay coils, whatever, in order to configure the antenna in different fashions from the ground. And this is just to show like the size of the spools of copper weld we're using. Again, just, you can see the lengths that we're drumming out are pretty significant. Typically, let's see, on average, going every even loading section, we're drumming out somewhere around 1,120 feet of conductor at a time, and that's on either side. So,
yeah, I would like to point out that we just didn't go down and get that conductor from the hardware store. We had to go out to the Mojave Desert and find long sections of demolished line with wire all laying everywhere in the desert and roll it all up. So every mile of wire that's up on the poles is the mile of wire that we rolled up out there in the Mojave Desert or in the Death Valley area. So, and it's the same thing with all the cross arms and the bolts and the insulators, we have to scan, large sections of the desert to find this stuff in pieces and what have you here and there, and clean all the debris up, for our landlord, the Bureau of Land Management, to abate the hazards and what have you involved. So basically, there's not only the putting together part, but there's the taking it apart part. So the overall effort here is about 3 times of what you're actually seeing get done, including, like in a previous video of dealing with a sprung spool of wire that you have to try to untangle while it's fighting you every inch of the way and all that. So I just want to point out that this is not a ham radio antenna project, and it's a major effort, and it's even more of an effort than the utility company itself had to go through, because they had all the right tools and everything was new, and that it was all requisitioned from the warehouse and came out of nice, neat new packages, but not for us.
many years in the making, lots of effort from very, whole multitude of different people. Eric and Justin spent a lot of time out in the desert glomming all of this stuff. So it's pretty significant what's gone into this at this point. Just to show, this is the pole 43. So this is where it was terminated before the pole pair. So this is just kind of showing that we're tying into the existing pole pair, finishing up the antenna structure. here I am with all the rigging equipment hanging off the belt before I'm climbing up the ladder, just all the stuff hanging off of you that can get snagged. So, you know, again, you have to be really cautious navigating all this. Another shot of the rigging equipment to set the tension. And here just to show how we tie the line in to existing, you know, what was already up there as far as the pole pair goes. And again, at a later point in time, these will actually have down leads that carry through those little ceramic rings, those bridle rings, down the pole into cabinets. So, and here we have pole 26. You can kind of see the ground, you know, the ground rod's buried under a pile of rocks there. But this is the end of the antenna section. So we've gotten the pole pair up all the way to the end. Of course, the outside pairs are going to need to go up at some point, but this is, you know, pretty significant what we've done here. And then, of course, this just shows that once you've tied everything on the dead end insulators, pulled your tension, you have to actually go back, climb up every pole, and tie off onto the insulators. So lots up and down. And, you know, it's just sort of a beauty shot of the desert out there. So, yeah, that's all we have as far as a slideshow. And there's one thing I wanted to point out too. If I have this correct, Eric, you brought up to me after we were done stringing up this pole pair that as far as the Alexanderson antenna goes, this is actually more developed than what you had at the Landers facility at this point. Is that correct?
Well, it's a greater length, and the Alexanderson antenna at Landers was only 880 feet long, but this one is 4,800 feet long. So it has much greater reception or transmission reception aperture than the Landers antenna. But unfortunately, the power company here has some massive zero sequence fault current flowing in the ground, and it may not be possible at all to receive out of the ground here, which is a massive tragedy. But at any rate, as a developmental or laboratory apparatus, we can still determine all of our propagation constants and loading and all of those things. And of course, outside of the ultra low frequency range, you know, the power line interference becomes negligible. So as a laboratory apparatus, it's invaluable to because the grounding system, when and if we can get the money to get the holes bored in the ground to put in the ground electrodes, will be much greater than Landers, because Landers, it was just simply ground rods driven into the trunk of a creosote bush using the roots of the bush as the ground, which actually was quite effective. But the loading sections were much closer, and you know, and the whole thing was much shorter. So this one will have much greater transmission characteristics, and it'll be more laboratory orientated, in that it'll be patchable and can operate in different modes. And like I say, it'll also be operating in the medium frequency band, which basically goes from 300 kilocycles to 3,000 kilocycles, and then that will be put on the internet in such a way that with an adapter box connected to your computer, you can actually hook your radio receiver, or whatever it may be, you know, some little solid state toy up to, you know, 100-pound World War II Navy VLF receiver, whatever it is, you will be able to connect it to this antenna and tune at will. And any number of people can do that, because it'll be isolated through each internet connection. And then on the other end, the cable TV shack end, that will be the ULF, the voice frequency, as we demonstrated with the 37 Bravo. And the objective now is to get that onto the internet. So we hope to have that accomplished by the end of the summer, and then that will be available on the internet in a way that you can listen to the signals, and also there'll be some kind of data logging function where for a subscription you can actually get all the graphs and what have you. And then thereafter, the next major global seismic event will be registered on this, and then that will quantify that this is actually viable means for studying earthquakes and getting a significant precursor to warn of the earthquakes coming.
Really looking forward to it.
So I think that's it. I'm not certain, but that's it for me.
Yeah, I don't have anything else, so it's pretty much it as far as update on what we've been doing.
Okay.
Awesome.
Nice work, Connor. It's good to see all that.
Thank you, man. Appreciate it. Well, you kind of got the whole thing going and trained me on all this, along with Eric, of course. But it's a group effort. All of us have helped out on some level with this project, and it's because of the collaboration and all these various personalities and skill sets involved that we're able to accomplish this at this point. So, it's worth acknowledging the team effort here.